students. Yeah. Listen. So today our topic of discussion is going to be an important one, which is called as, yesterday I told you, right? What is the topic we are going to discuss today? What is it? Can someone tell me? Guys, I need some response.
So we'll be starting with the power.
I called it as vertical circular motion, right? So the vertical circular motion wait, I'll show you this problem. Okay, so this problem is a concept which is based on application of the circular motion. Listen. So let's first read it like a question, then I'll explain the concept behind it. So there is a bob. Okay, bob is a small ball which is generally used in pendulum. Okay, bob of mass m is suspended by a light string. What do you mean by light string? So here the keywords I would like you all to make a note. So what is the meaning of light string here? It is massless. Means the string doesn't have any mass associated. Yes. It is imparted a horizontal velocity v0 at the lowermost point A such that it completes a semicircular trajectory. Trajectory means path. Semicircular trajectory in the vertical plane with the string becoming slack. So the meaning of slack is tension becomes zero at that point. Okay. With the string becoming slack only on reaching the topmost point C. So this is shown in the figure 6.6. Obtain an expression for V0, the speed at the points B and C, the ratio of the kinetic energy KB and KC at B and C. Comment on the nature of the trajectory of the bob after it reaches the point C. Okay. First, I want you to visualize what it means. Now, you guys tell me. Let's say I give you a string like this and a bob fixed to it. What will happen if you give velocity to it? Since it is fixed at this point, what will happen? The particle will try to take a curved path like this. Am I right?
Sir.
So, depending on how much velocity you are giving at this point, what will happen? This particular arc length will increase. Correct? See, for example, if you just push it and leave it, what will happen? It will go to this point and again come back. So observe, it will go to this point and again come back in this direction. Correct? Then what will happen? It will go in this direction and again come back in this direction. Correct? So this is the maximum end till which it is able to go. But what if you increase this horizontal velocity? Then maybe it can go till this point. Right? Then what will happen? The same thing will happen on the other side also. Are you able to understand what I'm trying to say? If you increase its
Yes, sir.
velocity, then maybe this kind of a scenario will happen. Like this, it can keep oscillating between different points. Now, if you give sufficient velocity to it so that the particle is able to travel and reach the highest point, then what will happen is whatever velocity it is having at this point will help it to complete the remaining circle. Okay. And this circle, since it is occurring in the vertical plane, this kind of a motion is what is called as vertical circular motion. Clear? So this is the observation. Now it is our job to tell what is the physics involved behind, what is the theory of physics involved behind all these things to happen. Can I rub the diagram? Okay. Now tell me what is happening at point A. So if I draw a free body diagram, what do you mean by free body diagram? This is a diagram which consists of only the string and the bob. So can I say that the tension at this point, if I call it as TA, it is acting because of the weight acting in the downward direction, and in this direction there is a velocity v0, right? Now tell me one thing, if the object is given a velocity perpendicular to the forces that are acting, what will be the trajectory of the particle followed? It is going to be a circular motion, right? So you're able to see that it is going in a circular motion. So for a particle to be in a circular motion, what is the necessary force? What is the necessary force required to put the particle in a circular motion?
Centripetal force.
Yes, which will act in which direction?
Towards the center.
Towards the center, which is m into v0 square divided by, what is the radius of the circular path?
The
Look at
length
the
of the
diagram.
string.
Very good. It is the length of the string which is going to act as the radius of the circular path. Now, at this point, can I say TA minus mg is equal to m into v0 square divided by L? Right. So TA minus mg is equal to m into v0 square, the whole divided by L. Right. Now, what is going to be the total energy at point A? What is the total energy at point A? If I take this line as the reference, the potential energy at point A plus the kinetic energy at point A. The potential energy at point A will be 0. What is the kinetic energy at point A? It is half into m into v0 square. Correct? So let this be equation number 1. Let this be equation number 2. Please note down till this point. So in this particular scenario, what we are going to do is we will be applying two concepts. What are they? One is Newton's second law. Second is energy conservation theorem. Now listen. At D, the string will be like this. It's going to be horizontal. So in this case, the tension at B will be in the leftward direction. Mg will be in this direction. If you observe one important point, I didn't take the tension of the string to be the same everywhere because the value of tension that is coming to picture depends on the action that is acting on the string. So in the case A, what is happening? It is because of this Mg that Ta is coming to picture. Whereas at point B, the Mg is acting in opposite direction. So what is the role of tension? Here tension is the one which is providing the necessary centripetal force, and here it is going to be m into Vb square divided by L. Clear? So Tb will be equal, tension at point B will be equal to m into Vb square the whole divided by L. Right, let this be equation number 3. Now tell me what is the total energy at point B? Now, what is going to be the total energy at point B? It is going to be mg into how much is the height raised by the object?
L, sir.
L. So the potential energy is mgl plus kinetic energy will be half into m into Vb square. So this is going to be the fourth equation. So I hope you guys are making a note along with me. So at point C, what will happen? Let's see if you guys are able to answer. Mg is acting in downward direction. Tc is acting in downward direction. M into Vc square divided by L is also acting in the downward direction. Now, what should be the equation for Newton's law? Mg plus Tc should be equal to M into Vc square divided by L. But what did they say? At point C, string becomes slack. Meaning of it is tension at point C is 0. Substituting it here, you get mg is equal to m into Vc square divided by L. M and M will get cancelled, which implies Vc square is equal to GL, or Vc is equal to root of GL. And let this be equation number 5. So at point C, our job was very easy. What did we do? By just using Newton's law, we got the answer for the velocity at point C, the speed of the particle at point C. It is root of G into L. Okay. Now, what is the total energy at point C? It is a potential energy at point C plus kinetic energy at point C, which implies the total energy at point C is equal to. What is the total energy at point C? It will be mg into, what is the potential energy, guys? Mg into, how much is this height?
12.
It is the diameter.
2L.
2L. So mg into 2L plus half into m into Vc square. But you know what is the value of Vc? Substituting it here, what will happen? So mg into 2L plus half into m into Vc square is g into L. Right. So it is 2 mgl plus mgl the whole divided by 2. What will be the answer? It will be 5 by 2 into mgl. What is 5 by 2 into mgl? This is the total energy at point C, and this is going to be equation number 6. Please make a note of it. Okay. So total energy at point C is 5 by 2 times mg into capital M. So that is equation number 6. Now see, since the particle is traveling under the influence of gravity. So gravity is what? It is conservative force. Right? Since the particle is traveling under the influence of gravity, what will happen? Energy conservation is applicable. So what can we say? Total energy at A is equal to the total energy at B is equal to the total energy at C. So what is the total energy at A, guys? Go revisit and see. It will be half m v naught square is equal to the total energy at B is mgl plus half m vb square will be equal to what is the total energy at C? It is 5 by 2 times mg into L. Now, if I take these two into consideration, half m v naught square is equal to 5 by 2 into mg into L. M and M will get cancelled, 2 and 2 will get cancelled, which implies V naught will be equal to root of G into L. Sorry, 5 into G. So they asked us to calculate this value, no? So V naught is equal to root of 5 into G into L.
Sir, can you please scroll up?
Sure. Is this enough?
I'll just
The voice is
take a
breaking.
screenshot, sir. Can you show at B? Thank you, sir.
Yeah. So V naught will be root of 5 into G into L. Okay. Now, what is going to be the value of VB? If I take these two equations into consideration, then MGL plus half into M into VB square pi by 2 times mg into L. Half mvb square will be equal to 3 by 2 times mgl. M and M will get cancelled, 2 and 2 will get cancelled, which implies VB is equal to root of 3 into G into L. So the velocity at point P is root 3 GL, velocity at point A is root 5 GL, velocity at point C is root GL. So V naught, that is VA is to VB is to VC is equal to root of 5GL is to root of 3GL is to root of GL. So it is nothing but root 5 is to root 3 is to 1. Okay. Now, what did they ask? What else did they ask in the question? So they asked what is V naught, the speed at points B and C, the ratio of kinetic energies at B and C. So how to find the ratio of kinetic energy at B and C? KB divided by KC is half into M into VB square by half into M into VC square. Cancel, cancel. M and M are gone. VB square is 3. VC square is 1. So answer will be 3:1. So velocities will be in the ratio root 3:1, whereas kinetic energies will be in the ratio 3:1. Okay. That's it. So I hope this concept is clear, right?
Yes, sir.
Okay. The next concept that we are going to see is the potential energy of a spring. So now the concept we are going to discuss is potential energy of a spring. So how to find the potential energy of a spring? Let's see. So you know how a spring works, right? So spring basically exhibits certain phenomena. What is it? It exhibits the property of expansion and compression. So what do you mean by expansion? Name itself suggests. So expansion basically means its length is increasing from its natural length. So what do you mean by natural length? Depending on the separation of windings, what will happen is if you add all those separations, then the length of that particular string when no load is suspended, okay, is what is called as the natural length. Okay. Now what will happen when you suspend a load? So what will happen when a load is suspended?
It will be expanded.
So when you say it is expanding, can you say that the relative distance between two windings will increase? Let's say
Yes.
its expansion is x naught. Okay. Now, if you remove this block, what will happen? The spring will go back to its natural length, provided it is not expanded beyond its elastic limit. Okay. Now the question is, how is it able to regain its shape? How is it able to regain its shape? It is because there is something called as, any idea guys, you want to answer and see?
Sir, elastic force.
Yes, that's right. That elastic force has a technical name called as restoring force. See, if you try to break the word restoring, storing means it will try to store it back to its original length. So there will be a restoring force acting, okay, where this restoring force Fr is observed to be directly proportional to x naught, where this Fr is the restoring force, x naught is the expansion or compression. Okay. Then, if you remove the proportionality symbol, Fr will be written as minus k into x naught. Here, minus sign indicates that it is a force. So the minus sign is coming because of the restoring nature of this force. Okay. And this k is what represents or something called as the spring constant. So k is called as the spring constant. So each spring will have a spring constant associated with it. Am I clear to this step, guys?
Yes, sir.
Now, what is our job? Our job is to find the potential energy of this particular spring. Now, I want you guys to answer me. Why is the spring going to have some potential energy? Why would it even come into picture?
Virtue of his position.
By virtue of it is because of the attempt we are trying to make in its shape. Okay, we are trying to change its shape. No, that is why there is a potential energy that is going to come into picture. But we know the fact that any energy that you're trying to speak about is always a consequence of the work that you do on the system. Okay, so again, what I'm going to do here is, for calculating the potential energy of a spring, I'm going to calculate the work done by the restoring force. Now tell me, what is the work done by restoring force between the points of natural length and instead of using the word points, I use the word instance, between the instances of natural length and maximum elongation or compression. Okay, so how to calculate it? Observe the derivation. Work done by restoring force. See, let's say at some instance the expansion is x. Okay, and from that x, let's say the restoring force is doing a small amount of work to compress it by a distance dx. Okay, it is trying to compress. So work done by restoring force to compress the spring by a distance dx. How much is it? dw will be equal to f into dx. So what is f here? It is minus kx, okay, into this dx. Am I right, guys? So if you want to calculate the total work done, what are we supposed to do? So total work done is equal to integral of minus kx into dx between the lengths 0 and x max. Okay. So minus k will come out, integral of x dx between 0 to x max. How much is it?
X square by 2, sir.
That's right. Minus k into x square by 2 between 0 to x max. Now what are we supposed to do? The place of x, substitute the upper limit minus the lower limit. So minus k into x max square the whole divided by 2. So minus k x max square by 2 is the amount of work done, and this is what is getting stored in form of elastic potential energy in a spring. So going forward, this is the formula that we are going to use. So it need not be x max square always. Depending on how much elongation they are given, the value of x max keeps changing from problem to problem. I'll do an example of a problem and show. But before that, write this point.
Sir,
Tell me,
why are we calculating it for instance?
why are we calculating it for?
A particular instance.
Where particular instance? Between two instances, natural length is zero expansion. Maximum elongation or compression is maximum. Beyond that, what will happen? It will lose its elastic property. If you try to expand the spring beyond its maximum limit, it will not regain its shape. Have you ever seen ball pens having some springs? Like
Yes, sir.
the click pens are there, right? They have springs in them. By any chance, have you ever tried to pull it away? Like you try to elongate it to the maximum extent and see. If you do it for small extents, yes, it will be able to regain its original shape. But if you try to do it beyond a particular point, let's say the spring is like this. You expand it lightly and leave, it is able to come back to its original position. You expand it even more and it is able to come back to its original position. There will be one particular position where you try to elongate it, it will become like this. Means the distance between the springs the windings will increase and it will not be able to regain its original shape. That is the reason why we try to calculate only within the elastic limit. That is why I called it as instances.
Okay, sir.
So please write it down.
So can you scroll up?
Let me know once you're done. Done, huh?
Yes, sir.
Okay. Now listen, we'll do a problem based on this. I'll tell you how to use this formula. Before that, I want you all to make a note. So here the negative sign indicates force is conservative in nature. Okay, here the negative sign indicates that the force is conservative in nature. Okay. So another example of conservative force is the elastic potential energy, that is, spring force. Spring force is conservative in nature. Now listen, if you try to draw a graph between the force and displacement, then you will get F is equal to minus kx. So the spring force is equal to minus of k into x. And if you calculate this area, then this area will give you the potential energy of that spring. Okay, this is a graphical representation. So area comes out to be minus k into xm square divided by 2. Here the area mathematically came out to be negative because it is below the x-axis. That is one of the mathematical reasons. But area is mathematics. The area in physics is work done. But work done here is nothing but the potential energy. I hope it is clear, guys. Right? Now, see. To simulate car accidents, you guys know what is simulation? Yes or no? You know what is simulation? Means something you try to do virtually using a software. Okay, or using some dummy devices, what we call it as simulation. To simulate car accidents, auto manufacturers, what they do is they study the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kilogram. Okay, there is a car of mass 1000 kilogram moving with a speed of 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant 6.25 into 10 power 3 Newton per meter. Then what is the maximum compression in the spring? Okay, I hope you guys read the question. Right? So they want to understand if the car is traveling with this much of velocity, then how much distance it will be able to travel, all those things. For that, they have some reason for doing that simulation. But here the simulation is done with respect to a car and a spring. What is the problem number? 6.8. Okay, car is moving and it has a mass of 1000 kilogram. It is moving with a speed of 18 kilometer per hour. Spring constant is 6.25 into 10 power 3 Newton per meter. Correct? Now you guys tell me, when the spring is experiencing maximum compression, what would have happened to the car? When maximum compression is done to the spring after it is being touched, what would happen to the car? At that instant, can I say something like this will happen? The car would have zero velocity. So initially, what is the energy possessed by the system? So here, when I use the word system, what am I trying to talk about? I'm talking about the car plus spring. So the car plus spring put together, if I call that as a system, how much is going to be the total energy possessed by it? Are you guys there or not, first of all?
Yes, sir.
So half into m into v square plus the potential energy of spring is 0. So this is the total energy which is initially present. So what is the final total energy? Kinetic energy of car is 0, whereas the potential energy of spring will be half into k into x max square. If you observe one important thing, I didn't apply the exact formula. I missed something. What is it?
Negative symbol.
I didn't put the minus sign because that negative sign should be used only when you use work energy theorem. Okay. Whereas when you talk about energy conservation, energy cannot be negative. Are you able to understand, guys? So that is the reason
Yes, sir.
why. Remember, whenever you are applying energy conservation, please make a note of it. Whenever you are applying energy conservation theorem, the sign of the energy need not be taken into consideration. Whereas, when you are applying the work energy theorem, yes, we need to take the sign into consideration. So half mv square is equal to half into k into x max square. So initial total energy is equal to final total energy, which implies half mv square is equal to half into k into x max square. Half and half are gone. So what is the mass? 1000 into velocity square is 18 is 5 square is equal to, I hope you understood why it is 5 square, because it is in kilometer per hour. Multiply with 5 by 18 is equal to k is 6.25 into 10 power 3 into x max square. 10 power 3 will get cancelled. So x max square will be equal to 5 square divided by 6.25. So 6.25 is 2.5 the whole square. So 5 into 5 divided by 2.5 into 2.5, how much will it be? 4. So x max will be equal to. So there will be a maximum compression of 2 meters in the spring.
Sir,
Please tell.
sir, why is the velocity 0?
Because it should stop. When maximum compression has happened, the car cannot travel beyond that. It is because of the car only, the maximum compression has taken place. Means whatever kinetic energy it had, it converted everything into what? The elastic potential energy.
Sir, once can you explain TEI and TEF?
TEI is the kinetic energy of the car plus potential energy of spring. So what is the kinetic energy of car before collision? It is half mv square. Plus the spring is neither elongated nor compressed, so it doesn't have any energy stored in it. When it is in relaxed position, why would it have energy? It is 0. Right? When the final situation, that is the maximum compression of spring has taken place, the car would come to a halt, and at that instant what will happen? Already the spring has got compressed to the maximum extent possible. So the energy will get stored in the form of potential energy. That potential energy is what I wrote it as half into k x max square.
Sir, why is total energy is equal to the kinetic energy of car plus potential energy of spring?
Because it's a system. That is a system. System means whatever you are trying to study. Here it is a two object system. One is car and the other is spring.
Can it be potential energy of car plus kinetic energy of spring?
No, it cannot be, because the potential energy of car is always going to be 0. Because you're taking that as reference. If you want, you can take that also. It will get cancelled on both the sides. Because initially and finally, it is on the same level only. When it is on the same level, it has the same potential energy. Are you able to understand what I'm trying to say?
No, sir.
If I take this, when will the potential energy of car change? Only when it is jumping. Is the car jumping here?
No, sir.
Then what is the necessity to take that potential energy? If you want to take it also, with reference to if you take the ground as a reference, its potential energy is going to be 0. We need not even consider. Right?
Yes, sir. Sir, then kinetic energy of the spring will also be 0.
There is no spring will not have any kinetic energy because it's a massless spring. Any object will have kinetic energy only when its mass is there. The spring that you are considering, nowhere they would have spoken about mass. Okay.
Okay, sir. Understood.
So there is no concept called as kinetic energy of spring unless the spring as a whole is moving. If that kind of a scenario occurs, then the spring should be an object having mass, or else it is not applicable. So the maximum compression that can take place is 2 meters. Okay. The reason why I applied energy conservation here is because they use the word smooth surface. So smooth surface is conservative and spring itself is conservative. Okay. Whereas if I try to solve the same problem using work energy theorem, observe the approach. When I use work energy theorem, what does the statement say? Work done by all forces is equal to change in kinetic energy. So here, who is having the kinetic energy?
Car.
It is the car. So what is the work done by all the forces? That is work done by car, which is nothing because it's moving on a smooth surface. So there is no work done by the engine or something we are going to talk about, right? So who is the only component that is doing the work on the car? It is a spring. So work done by spring is equal to change in kinetic energy of the car. Means the spring is the main reason for its kinetic energy to change. So what is the work done by the spring? It is half into k into x max square. Observe carefully. Here I'll put a minus sign because it's doing a negative work. Right? I told you, right? Whenever you are applying work energy theorem, you need to take the minus into consideration. This will be equal to, what is the change in kinetic energy? Final kinetic energy is 0 minus initial kinetic energy is half into m into v square. Now observe this equation and the above equation are the same. Half into k into x max square is equal to half into m into v square. Half and half will get cancelled. Now you solve. It's the same story. So you're able to understand? I could apply both energy conservation and work energy theorem with this problem because the whole system is acting under conservative forces. But if you see the next part of the question itself, they would have changed something. The next question is, consider example 6.8, taking the coefficient of friction of the surface to be 0.5. Now calculate the maximum compression. Right. So previous case, the car was moving on a smooth surface. Whereas now what is happening? There is a friction acting on this object. What is the value of friction? Friction is equal to mu into n or mu mg. Correct? Now can I apply energy conservation in this case? Energy conservation is not applicable.
Yes, sir.
Because of friction. So I have to apply only work energy theorem. So when I apply work energy theorem, I will add an extra work done by the friction also. So minus half k into x max square plus the friction is doing a work of how much? Minus mu mg into the displacement is x max. Guys, am I clear?
Yes, sir.
This should be equal to minus half mv square because 0 minus half. Right. So first thing, minus will get cancelled. Now what will you get is k into x max square plus 2 times mu mg into x max minus mv square is equal to 0. It is actually a quadratic equation in x max. When you solve this, you will get a positive value and a negative value. Positive one is going to give you the answer. So it is like the 6.25 into 10 power 3 into x max square plus 2 into mu is 0.5 into m is 10 power 3 into g. For the time being, I'll take it as 10 into x max minus m is how much? Again 10 power 3 into v square, that is 5 square is equal to 0. So 10 power 3 first gets cancelled. Okay. 2 into 0.5 is 1. what will happen? 6.25 into x max square plus 10 into x max minus 25 is equal to 0. All are divisible by 5. Simplify and then solve. You can use the formula minus b plus or minus root of b square minus 4ac by 2a. Quadratic equation formula. As I told you, you will get two values of x max. The one which is negative should be ignored. The one which is positive should be taken into consideration. Because x max is length, length is distance, distance cannot be negative. Clear, guys?
Sir,
Tell me.
sir, if the string is massless, then how is it having potential energy?
The potential energy it is having because of its spring constant. First thing in your mind, I'm able to understand why you have this confusion. Potential energy formula is not mgh. mgh is called as gravitational potential energy. Shariya.
Okay,
Other
sir.
objects will also have elastic potential energy is half k into x max square. It is because of the spring constant. Spring is having an energy associated with it called as potential energy. What is the name of it? What potential energy does spring possess? It's called elastic potential energy.
Okay, sir.
Okay. Be careful. So, did anyone calculate it by any chance? So, before we calculate, tell me, should the value of x max be greater than 2 or less than 2? Which one is right? Think logically and tell me. Should you get a value which is great? Why did I take the 2 as a reference? Because the previous problem we got the answer as 2. Do you think the answer will be greater than 2 or less than 2?
Greater than 2, sir.
It should be less than 2. Again. Because in the previous case there was no friction. Correct? Because there was no friction, the object was able to travel a longer distance. Means after the car has touched the spring also, the car has also traveled a distance of 2 meters before it came to rest. But now what is happening? So in the previous problem, only spring was trying to stop the car. But now, along with spring, who else is also trying to stop the car?
Friction.
Friction, right? So the car will stop even before 2 meters. See, for example, you're running, there is one person trying to stop you, right? You can push that one person to a certain distance and stop. If two people are trying to stop you, you can still try to push them, but not to the extent to which you did when it was one person, right? You're able to understand what I'm trying to say.
Yes, sir.
Yes,
So
sir.
same logic. So that is why let me check the answer. See, value should be less than 2, 1.35. Whereas in the previous case, it was 2. Okay. So this is all based on spring. Tomorrow we'll do one more problem based on spring from the additional exercise. I'll show you the problem also. There's a problem. We'll do this problem, revise this concept and come, and then we'll go to the next important topic that is called as collisions. Okay.
Yes, sir.
Any other doubt?
No, sir.
Okay, then we can wind up, guys.
Thank you, sir.